sunbeam propulsion. How NASA could reach Alpha Centauri in just 40 years. For generations, interstellar travel has belonged to the realm of science fiction, an unattainable dream confined to the pages of novels and the scripts of spacefaring epics. The vastness of space, with its incomprehensible distances, has always seemed to place the stars beyond humanity's reach. But that could soon change. NASA is now working on an extraordinary new propulsion technology, sunbeam propulsion, that could allow us to reach Alpha Centauri, our closest neighboring star system, in just 40 years. Yes, 40, not 70,000 or 100,000, as current chemical rocket speeds would require. This would mark a revolution in space travel. It would be humanity's first real step into the interstellar age. But how could this possibly work? What engineering breakthroughs are being proposed to make such speeds feasible? And most importantly, will we finally be able to explore planets like Proxima b and K2-18b, worlds that might actually harbor alien life? Let's take a deep dive into NASA's sunbeam propulsion concept and the future it could create. Milky Way, the Great Barrier. Why interstellar travel has eluded us. The scale of space is both majestic and merciless. The fastest spacecraft ever built, the Parker Solar Probe, is hurtling through the solar system at a blistering speed of 692,000 kilometers per hour. That's fast enough to circle Earth 17 times in 1 hour. And yet, in the context of interstellar travel, that's not even close to enough. Let's put things in perspective. 1 light year equals about 9.46 trillion kilometers. Proxima Centauri, the closest star to Earth beside the Sun, is 4.24 light years away. K2-18b, an exoplanet in the news for potentially harboring signs of life, is 124 light years away. Our current technology would take tens of thousands of years to reach even the closest of these targets. Even the Voyager 1 spacecraft, which has been traveling through space for nearly 50 years, has yet to reach a single light day in distance. Clearly, to become a true interstellar species, we need a radically new approach to space propulsion. Shooting star, the cosmic temptation. Signs of life on K2-18b. In recent months, our cosmic curiosity has been reignited by groundbreaking news from NASA's James Webb Space Telescope. This powerful instrument recently detected dimethyl sulfide DMS in the atmosphere of exoplanet K2-18b, a molecule that on Earth is produced exclusively by living organisms, primarily phytoplankton. This discovery is the strongest biosignature evidence we've ever found outside our solar system. K2-18b is believed to be a Hycean world, a planet with a hydrogen-rich atmosphere and a vast global ocean. If these characteristics hold true, this ocean world could very well be teeming with alien life, swimming beneath its hazy atmosphere. But confirmation requires more than distant telescopic observation. We would need to go there, to send a probe, to observe, to explore. Globe showing Europe, Africa, Proxima b, the first step to the stars. While K2-18b stirs the imagination, Proxima b offers a far more reachable target, at least by interstellar standards. Discovered in 2016, Proxima b is an exoplanet orbiting Proxima Centauri, the closest star to our solar system. It's located just 4.24 light years away, nestled in the Alpha Centauri triple star system. It lies within the habitable zone of its red dwarf star, meaning liquid water could exist on its surface. However, Proxima b is tidally locked, meaning one side always faces the star in eternal daylight, while the other is trapped in perpetual darkness. Yet there may be a twilight zone in between, where conditions are mild enough for life to thrive. But here's the challenge. Even this closest of alien worlds is still unreachable using today's technology. A conventional probe would take 70,000 to 80,000 years to arrive. That's where Sunbeam comes in. High voltage, the Sunbeam propulsion concept. A new dawn for space travel. NASA's Sunbeam propulsion system could be the key to turning centuries into decades and dreams into missions. The concept is both bold and brilliantly simple. Instead of carrying fuel on board, the spacecraft receives a continuous beam of energy from an external source, allowing it to accelerate constantly during its journey. At the core of this system is a relativistic electron beam, a stream of electrons accelerated to nearly the speed of light. This beam transfers momentum to the spacecraft, pushing it ever faster as it travels. But where does this beam come from? Sun, the solar station. The plan is to place a solar station, a large platform, near the Sun, where it can harvest vast amounts of solar energy. Using solar magnetic fields and radiation pressure, the station would remain stable while firing a focused electron beam at the outbound spacecraft. This station is more than just a power source. It's the interstellar fueling station that will accelerate the probe to 30,000 kilometers per second, 10% the speed of light. At that speed, the probe could reach Proxima b in just 40 years. DNA how it works, physics and engineering of the sunbeam drive. The system relies on a mix of relativity, plasma physics, and cutting-edge engineering. Relativistic electrons are used because they carry immense momentum and energy, even though they have little mass. As they travel at near light speeds, Einstein's time dilation kicks in. This slows the spreading of the electron beam, keeping it tight and focused over interstellar distances. This effect is related to what physicists call the pinch effect, which helps maintain the beam's coherence as it travels. The beam does not carry fuel, but it transfers force. As long as it hits the spacecraft, it provides a steady push, allowing the craft to accelerate without carrying massive propellant tanks. It's a genius workaround to the tyranny of rocket equations, which limit how far and fast we can go with conventional engines. Microscope why this is better than other concepts. Sunbeam propulsion isn't the only interstellar idea on the table. The Breakthrough Starshot Initiative, backed by figures like Stephen Hawking and Yuri Milner, proposes sending tiny chip-sized probes attached to light sails, pushed by massive Earth-based lasers. That approach is cheaper and could be deployed sooner, but it has limitations. Microprobes can only carry minimal instrumentation. There's no room for cameras, communication gear, or shielding. In contrast, NASA's Sunbeam probe is envisioned as a 1,000 kilograms full-scale spacecraft, capable of carrying real scientific payloads to other star systems. It could collect samples, image alien worlds, and send back high-quality data. Hourglass not done, the challenges ahead. As exciting as Sunbeam is, it's not without hurdles. Key technical challenges include maintaining beam alignment over interstellar distances. A tiny miscalculation could cause the probe to drift off course, and the beam to miss entirely. Generating and focusing a relativistic beam for extended periods. Building a solar station that can survive the intense heat and radiation near the Sun. Developing thermoelectric converters that can efficiently turn solar heat into electricity at extreme temperatures. Right now, some of these technologies exist only in theory. But we are making progress. The Large Hadron Collider already produces beams with higher energy than Sunbeam requires. Beam control technology from particle accelerators could be adapted for space. And missions like the Parker Solar Probe have shown that we can build spacecraft that survive close solar flybys. Compass, when will Sunbeam launch? The million-dollar question. When will we launch the first Sunbeam probe? Even in the best-case scenario, it will take 20 to 30 years to develop the required materials, power systems, and beam guidance technologies. The solar station itself would require a decade of testing and construction, possibly involving new advances in space manufacturing and AI-controlled positioning. But the groundwork is being laid. And once this system is operational, the floodgates to interstellar travel will open. We will finally be able to send real probes to real planets around other stars, not in the distant future, but within the lifetime of our children and grandchildren. Glowing Star, a new cosmic era. Sunbeam propulsion is not just another engineering experiment. It's a paradigm shift. The same way the rocket engine made the moon reachable, Sunbeam could make the stars attainable. For the first time in human history, interstellar travel is moving from fantasy to feasibility. Imagine what we might find: alien oceans, exotic life, a second Earth.